The final lecture today will finish off our discussion about ranks of sets in the well-founded hierarchy of sets, the V-alpha hierarchy. This will be the last lecture, and we'll finish with a discussion about how we can widen out the recursion theorem on ordinals to actually be a recursion on all sets, now that we've got them nicely laid out in the well-founded hierarchy. So this is what we'll do next. So we'll proceed here then to lemma 6.5 on page 63. So lemma 6.5. So the first part, again, it's a rephrasing of things that we've already know or have defined. For any set in V, it's got a rank, the least ordinal, where X is a subset of V alpha. So the elements of V alpha are going to be those sets which have got a rank less than alpha here. 2 says, for X in V, then for all Y in X, Y is in V, and it's got smaller rank. This accords with our picture of thinking that we can't build the set X until we have all the elements. So the elements of X will appear at earlier stages in our layers of the cake than the set X itself that's here. Notice we say if X is in V and any Y in X, Y is also in V. The axiom of foundation, of course, makes this redundant. It implies that all sets X are in V. But actually, I can make this definition of the V alpha hierarchy without appealing to the axiom of foundation. So this actually makes sense, as does the line above, even without assuming the axiom of foundation. Then we'd be just talking about the sets that are in V. But as I said, we shall assume the axiom of foundation. So again, if X is in V, then the rank of X is just the supremum of the rank of Y's plus 1 for Y in X. And this is the strict sup of the rank of Y's for Y in X. Sorry, this is a plus here. So, well, we'll comment on these as we go. So let's look at the proof of 1. If X is in V, then what do we have? If its rank is less than alpha, this means there's some beta smaller than alpha, which is its rank. Beta, the rank of X being the smallest beta for which it's a subset. So I can just say there's a beta less than alpha, which X is in V beta plus 1. Because after all, this is just the power set of this. But beta less than alpha means beta plus 1 is less than or equal to alpha. Because V beta plus 1 is contained in V alpha. This is lemma 6.4, 2, which said that the V's are accumulating. If I have gamma less than delta, V gamma is a subset of V delta. And that's all we're using here. Beta plus 1 is less than or equal to alpha, so V beta plus 1 is a subset of V alpha. So rank x less than alpha is equivalent to x being in V alpha, which is just this statement here of 1. So this finishes 1. So let's look at 2. So let's call alpha the rank of x here. So x is a subset of V alpha, but not of anything smaller. So if y is an element of x, right, then y is a member of V alpha. That's what this says. Right? Hence, right, by 1, the rank of y here then is less than alpha, which is the rank of x. Right? Because V alpha is the set of things, the set of y's whose rank is less than alpha. So here's y in V alpha, its rank is less than alpha, which is the rank of x, which is just what we wanted here. So that finishes 2. Okay. Now, 3. So the first thing to note is that actually this equality here is actually nothing to do with our situation about sets in V or V alphas. It's just to do with the definition of what strict sup is. Right? Recall that the strict sup of a set of ordinals is the least ordinal, which is strictly bigger than every element of the set. So if there's no largest element of the set, then that's just the same as the supremum. On the other hand, if the set of ordinals has got a largest element, this is supposed to be the least thing bigger than everything in it, then if this has got a largest element, the strict sup is that largest element plus 1 in order to be strictly bigger. And that's actually just what this says over here. Right? The supremum of a set of ordinals, right, is then supremum of a set of ordinals plus 1 is going to end up as this strict supremum here. So this equality is nothing to do with our V alpha situation. So note first that the second equality is just the definition and meaning of strict sup. Sorry. Note first that the second equality is just the definition and meaning of the strict sup here. So it's the first equality that we concentrate on here. It's convenient to use this idea. Okay, so let's name the rank of x as alpha here. Sorry, no, I'm starting out wrong. Let alpha be this here, and we'll show it's this. Let alpha be the strict sup of the ranks of the gadgets inside X. Now, part 2 says the elements of X here have smaller rank than that of X. So by 2 here, if y is an element of x, y is in some, if y is an element of x, then the rank of y, well, it's certainly less than the rank of y plus 1. Okay? And this is going to be less than the rank, less than or equal to the rank of x. All right, so the rank of y is strictly less than the rank of x. So add 1, it's less than or equals. So the strict sup here, the least thing greater than all of the ranks of its elements, this is then a candidate for it here, right? But alpha is supposed to be this. So alpha is the strict sup here of these rho y's. This must be less than or equal to rho x. So what we're trying to show is that alpha is the rank of x. So we've got the inequality in one direction here. We need the inequality in the other direction here. So then by 1, for each y in x, right, I've got that rho y less than rho y plus 1 being less than or equal to alpha, implies then that y is a member of E alpha here. And this was for any y in x. So thus x is a subset of E alpha here. So the rank of x is less than or equal to alpha. The rank being the least alpha primes, is that x is a subset of V alpha prime. So I have the inequalities in both directions. So then alpha equals rho x here, which is just what we were trying to show here. That this strict sup here is rho x. So this finishes 3 and the lemma. So this kind of encapsulates, again, quite a few facts that we've talked about for our V alpha hierarchy. Let me draw the picture again one more time. Ordinals up the middle. So this may be some ordinal alpha here. I've got x, perhaps here is its elements spread out here. And this is V alpha. So I have that x is contained in V alpha. So here is its elements, here are the y's that go to make it up. They occur at earlier stages. So this is the basic picture to have here. Right? What the next lemma does is give us particular information about how many ordinals each of these V alphas has got. And it turns out that the ordinals of V alpha are precisely the ordinals of alpha, which is neat. Okay, so let's then look at 6.6. So lemma 6.6 here. The first clause says that rho of alpha is alpha. So that's immediately going to give one direction of this equation that says the ordinals of V alpha are precisely alpha. What does rho alpha equal alpha say? It says that alpha is a subset of V alpha. So that's immediately going to give us this subset direction. But in fact, there are no more ordinals in V alpha than there are in alpha. So proof here. So we assume by induction we know this for smaller beta. For beta less than alpha, we've got the result. The rank of beta is beta. And what we want is the rank of alpha is alpha. Okay, so by 3 of the last lemma, what did we have? We had that the rank of a set, in this case we're going to look at the rank of alpha, is the strict sup of the rank of its elements. And by the inductive hypothesis, these all are their own ranks. But now the strict sup of the elements of an ordinal is that ordinal itself, irrespective of whether it's a successor or a limit ordinal. And that's actually why we don't need to divide into cases whether alpha is a successor or a limit core, because we're using a strict sup notation here. If I'd just been talking about ordinary sups, I'd have to back up and say, oh, maybe alpha is a successor, maybe it's a limit. But it's neat to have two cases combined by taking strict sups here at this point. And it gives us what we want. Rho alpha is alpha. So that's one neatly disposed of. So 2 here. I've said already, if alpha is its own rank, this means alpha is a subset of V alpha. So this comes directly from 1. And we need the other inclusion. Here. Okay, pick a beta that's over here. V alpha is the collection of things of rank less than alpha. But by part 1, the rank of beta is beta. So beta is less than alpha. But that's exactly what we wanted to show. Any ordinal in here is a member of alpha, which is what we have here. Hence, the other inclusion. So this finishes 2 there in the lemma. So what we have with the V hierarchy is this nice, well-ordered, literally, picture of where sets appear. So it means, in fact, that for the epsilon relation is a well-founded relation on sets. So this is kind of a very useful, as I said, a useful property to have for our sets. For example, it means that we can prove things about all sets by induction. So we previously used induction along well orderings, so well-founded relations that are total, that are linear. So we know this from natural numbers, and we've shown this also for ordinals. But actually, you've got induction along any well-founded relation, even if it looks like a partial order. As long as it has this property that any non-empty subset of the field of the relation has a minimal element, then you can do a principle of induction for that relation. So we're going to look at that next in the case just of epsilon. And once you've got a notion of induction, then you can also prove theorems by recursion. Right? So we can then define by recursion functions on all of the sets of mathematical discourse by so-called by epsilon recursion rather than recursion on ON. So we'll look at these results then here to finish off. So on page 64 at the top here, lemma 6.7. So principle of epsilon induction. So now let phi be any well-defined and definite property of sets. Then, well, I've written it out in two forms, as kind of a set form and a form for proper classes, although there's little difference between them. So here's the set version here. Suppose I've got a transitive set, X. So it says, for all y and x, suppose the following holds. That for all z and y, if phi of z holds, this implies phi y holds. So what is this antecedent going to say? We're going to have an implication here. This is going to say, right, right, if y inherits the property phi, given that all of its elements have property phi. So sort of like proceeding upwards, right? If all of the things below y in the epsilon ordering have property phi, so does y. So if this here is true, right, for all of the elements y and x, right, then the conclusion is for all y and x have property phi. Okay, so to repeat, if the elements of x can inherit the property phi from their members, if all their members have it, then all elements will have it. Now the class or V form just says this about V rather than X. So it'll be the same statement, except I just don't restrict to X here. I talk about all sets Y. And the rest of the statement then is the same. Then the conclusion is every set in V has property phi. And the proofs are pretty much, well, exactly the same, really. It's just a question of whether you want to talk about transitive sets or the whole of the transitive universe V. And the same maneuvers, right, will give us these proofs here. So let's look at the set form. I just prove the set form and say why it's like this one. So suppose this didn't hold, right? Then there'd be objects in X for which phi Y failed. Okay. So let Z be the collection of Y's in X such that phi of Y fails. So we'll prove a contrapositive. We'll suppose that Z is non-empty and show that this must be false. So we prove a contrapositive by assuming that Z is not empty and show that the antecedent, so the hypothesis over here, is false. So proving this implies this is the same as proving not this implies not that. So now we do use the axiom of foundation. Z is non-empty, so by the axiom of foundation, it will have an epsilon minimum element. So Z is not empty. There's Y0, an epsilon minimal element of Z here. So recall that means Y0 intersects Z is empty. Right? So there's nothing that's epsilon in Y0 that's epsilon in Z. So it's epsilon minimal. And you can kind of see it coming. This means that all the elements of Y0 are not in Z. So all the elements in Y0 have got property phi. But the antecedent says over here, if all the elements in property Y in Y0 have got property phi, then Y0 should have property phi. That contradicts the fact that Y0 is in Z. So this fails. And our contrapositive is proved. So I just have to write that down now. Okay. So then, right, for any x in y0, note that, any, better use another letter, u in y0, right? U here is a member of x because x is transitive. Because x is transitive, we have y0 in x implies that y0 is a subset of x. By the minimality of y0, phi holds for these u's. But this is true for any element of y0. So then we have, for all u in y0, phi of u. But the antecedent would say if it held, would say for u in y0, phi of u implies phi of y0. So here I've got P, and I got P implies Q, so therefore I've got Q. So we deduce phi of y0. So here's P implies Q, and we deduce phi of y0. Right? But y0 is in Z. Z is the collection of things on elements of X where phi fails. Right? So the antecedent fails, and we get our contrapositive. Is false. And we're done here. So actually the proof of 2 is so much the same, there's no need to really write anything further out. All we would do here is define Z here to be the collection of y's in V, for which not phi y holds. But again, by applying the axiom of foundation, I'd be saying again, right, if Z is non-empty, there'd be some epsilon minimal element, y0 of Z. And all of my other argument is exactly the same. All I've done is just change this here. So if you look in text, you may see either forms written down here. But this is kind of useful if you want to prove something about all sets right here. So let's finish that one. 6.7. So as I said, if we've got a principle of induction, then we'll have a recursion theorem to go with it. So this is 6.8. Theorem 6.8, the epsilon recursion theorem. So this will be our first recursion theorem where we do a recursion on a partial order, which is well-founded, rather than a linear strict total order, which is well-ordered. But there are features that are familiar. I've got a function from V to V, so function from sets to sets. So let this be any function here. Then there is a unique function H, now defined on all sets, rather than just On or omega. Okay. So that for all x, h of x is going to be g of h restricted to x. Right, and in the text it spells out exactly what this is. Right, this is g of the set of ordered pairs y hy here for y in x. But more neatly written out as just h restricted to x. This is just h applied to the members of x. Okay. So function set of ordered pairs, this is h restricted to x. So again, the same sorts of things could be said. H of the empty set is G of, well, H restricted to the empty set is just the empty set. So and this is the kind of thing that we've seen before. This is the empty set. So that's how H starts out at the bottom of the V hierarchy on V0. It just returns G of the empty set, but that's all right. G is defined on all sets here. Now, actually, I'm going to spare us the proof here. So proof is, you can omit. Okay. But if you are interested, do read it. You'll see there are many things that are exactly like the proof of the transfinite recursion on On. We define the function h as a union of a collection of a proper class collection of approximations. And we show the uniqueness of h in exactly the same way as before. Okay, so I just say it's omitted, but similar features. To the proof of recursion on On. Here. So it gives us a way of defining functions on sets. So I'm in an example. It guarantees that there's a unique function which does this. Right? I mean, it's kind of too simple to think about. I mean, all of our ordinal recursions are examples of epsilon recursions. So this can be thought of as a definition by epsilon recursion, as a special case of a definition by epsilon recursion. I mean, there's no help in thinking of it that way, because I'd have to define a function g that for things that wasn't ordinals would default to 0, or the empty set, and so on. So there'd be nothing really to be gained thinking of it in this way, right? But I can envisage, if I want, to think of ordinals, recursion on ordinals as a special case of epsilon recursion, right? Here. Okay, let's, so in the time that's left, let me do another exercise also here. Let's go back to exercise 6.5. So essentially this finishes our theory here for the course. Right? Right, you may be glad to know. Okay, let's look at exercise 6.5, which is about well-foundedness. So here, let phi be the proposition there is a sequence of sets x sub I here for I in omega with xi plus 1 being a member of xi. So what is phi saying? Phi is saying there is no descending epsilon chain. If there were such a sequence like this, I'd have, x0 had x1 as an element, which had x2 as an element, which had x3 as an element. And so I'd have here that there's a descending epsilon chain like this. So in particular, the epsilon relation below x0 would certainly not be well-founded. So by particular, the axiom foundation, this would mean x0 could not be in V, right? Because the epsilon relation is well-founded on any set in V. So the exercise says, show that phi just follows from the axiom of foundation. That's part A. Part B says that actually phi, together with the well-ordering principle, implies the converse. So it's not exactly equivalent to phi, the axiom of foundation. But it is if you allow yourself to assume the well-ordering principle. So if I think of the well ordering principle as true in the background, this is equivalent to the axiom of foundation. Okay, so let's see what we would say here. So let's look at A then first, right? And you can actually perhaps see quite quickly that if phi failed and there was such a sequence, we would not have we would have an ill-founded set. Okay. So my solution then here is for A. Suppose xi here, this was such a sequence. Then we show phi fails. Then we show axiom of foundation fails. Well, I could just look at this set here, the set of the xi's. And you see straight out, there is no epsilon minimal element. It can't be xi because xi plus 1 is a member of xi. So because there's an infinite descending chain, that just says it. There's no epsilon minimal element here. So that's just what foundation says. Every set should have an epsilon minimal element. So not axiom of foundation. So perhaps more interesting is B here. What was B? Assume there's no infinite descending, assume there is no infinite descending chain and assume the well ordering property. Then the axiom of foundation is true. So let's assume WP here. Suppose the axiom of foundation fails. So again, we'll do a contrapositive. We'll assume not axiom of foundation, and we'll prove not phi, meaning that there is such an infinite descending sequence of sets xi. So we have to construct an infinite descending sequence, or we have to choose elements xi, xi plus 1, xi plus 2, and so on. And again, the word choose here is a flag that we're going to need the axiom of choice, or in this case, we'll assume the well-foundedness property. So suppose X witnesses a failure of the axiom of foundation. we assume X has no epsilon minimum element. Okay. So let's call X X0 at the top of our chain here that we're going to think about. So since X is not well-founded, it's not the empty set, so it's got something in it. Pick, choose, whatever word you want to use, pick an X1 in X0. By assumption, X has no epsilon minimum element, so this X1 must have elements in common with X. Okay, by star here, there must be X2 in X1 and in X0. Right? So we pick one. And again, we're just going to continue this argument here. Repeat. Again, by star, there must exist some X3 here, which is a member of X2 and in X0. Okay. Choose an X3. So by infinitely many choices like this, so by repeating this argument and appealing to the axiom of choice, right, we can choose an infinite descending sequence. Right, xi plus 1, element of xi, for I less than omega. In other words, not phi. Right? In other words, not phi. So from our assumption, not axiom of foundation, by allowing ourselves infinitely many choices, right, here we deduce not phi. So this gives us the contrapositive and finishes B. Right? So this finishes B in the exercise here. Okay. Okay, fine. So that finishes the last lecture here. There'll be some revision sessions coming up in which I'll send you an email about. I do hope you found this interesting. Admittedly, it's slightly strange doing this all on the internet, online in this way. If you're staying for the 4th year, do consider taking the axiomatic set theory course, which I teach as well. In that course, we look and see how Gödel showed that the continuum hypothesis was actually consistent with the axioms of ZF. And he also showed at the same time, by the same construction, that WP, or the axiom of choice, is consistent with the axioms that we've been discussing. In other words, he showed that both AC and the continuum hypothesis were kind of safe assumptions for mathematicians to use. He showed that there were no more inconsistencies in mathematics if we assume AC or WP than there are already consistencies there, if any. So We will not introduce inconsistencies by assuming AC or the continuum hypothesis. And that's the major task of the fourth year course in axiomatic set theory. So I'd be very happy if you went on, if you're staying in the fourth year and you went on to take that course. So at this point, I'll wish you luck and say goodbye, though of course, I really want you to come along to the revision classes and send me suggestions of what you would like me to do, what you'd find most useful there. So I'll just say goodbye for now then. Goodbye.